Guys, hello, can you hear me? All right.
Yes, sir. Yeah.
All right.
Thank you.
Okay, then we can move on to power distribution in full AM. Power distribution in full AM. All right, so normally the power actually is proportional to the square of its amplitude. All right, normal. All right, the absolute value or the power value normally proportional to the square of its amplitude. Then if I would like to determine the power distribution in full AM or double sideband large carrier, then I need to recall the general expression, all right? General expression of double sideband large carrier or full AM signal, which is this one, which is same actually, but I multiply, if you remember, this one. All right, this is the general expression. Then if I multiply inside, then I will have a sub c cosine with carrier frequency plus 2 sinusoidal signal, one with frequency for modulating signal and one for the carrier signal. All right, then same goes for this one. If I multiply, then I will have the first term, which is carrier, and after that, if I multiply 2 sinusoidal signal, and from the relationship, all right, cosine A times cosine B, then I have this result, all right, which is same the one that we have done here. All right, you can see this one, the relation, and this is two terms, one for upper side and one for lower side. So the power, actually I have power here in carrier frequency, and I have power in both upper side band and lower side band. All right, then as I mentioned, the power actually is proportional to square of its amplitude. Then the power at the carrier will be this is the amplitude, will be a sub c squared. All right, k actually is a constant for the what you call it, the proportional constant. And for sideband power, the power will be same. Why? Because this one actually we have same amplitude, all right, but one for upper sideband and one for lower sideband. Then the power will be the squared of its amplitude, which is m a sub c divided by 2. Then we have m a sub c divided by 2 squared, and we have the proportional constant. All right, so we have power in this carrier, which is this power, and carrier for upper sideband, which is this power, and lower sideband, which is this power. All right, so we have three terms. Okay, then if you'd like to calculate the total transmitted power, all right, total transmitted power, as you can see, the summation of power in the carrier, all right, power upper side band plus the power in lower side band. Here, so we have a sub c as a constant. You can see k a sub c squared and k up sub a sub c squared, which is a common. Then I can take it out. There will be 1, which is the power inside the carrier, m squared divided by 4 plus m squared divided by 4, which is the power that located in both upper sideband and lower sideband. All right, so this one will be squared and this one will be squared. So we'll have m squared divided by 4 and m squared divided by 4. Then we can simplify it. This one will be k a sub c squared 1 plus m squared over 2. This one plus this one will be m squared plus 2, and this one can be replaced by p sub c. All right, p sub c, which is the power for carrier, as we can see. All right, 1 plus m squared divided by 2. So this is the total power. All right, total power or power distribution if we deal with double sideband large carrier. If we are dealing with double sideband large carrier, then this one will be the power distribution. Okay, then here we have some notes that's related to the power itself. All right, so a transmitter is a power limited So that means more powers means large device, and too much power causes also interference with the nearby stations. All right, so this is, I mean, it's very obvious in communication, any communication system, there is a trade-off. All right, there is a trade-off between power and interference. All right, power and interference. So if I keep increasing my power, definitely I will generate more interference to adjacent frequency or to nearby or to adjacent stations. All right, so that means there's a limitation. Okay, so that's why we have what we call it signal to interference noise ratio. All right, in communication system we have a ratio, we call it signal to interference. That means the signal, when I said signal to interference, that means the power of the transmitted signal divided by the power of the interference. All right, so this one actually that reflects the relationship between the power and interference. All right, so again and again there is some limitation. I cannot keep increase the power. All right, because if I keep increase the power, definitely the interference will increase and the capacity gonna decrease. All right, then what else? All right, so the receiver extracts the original information from the signal power that it's received, as we will see from the demodulator, how we can demodulate or how we can detect. Definitely the greater the received power, the easier it is to recover the desired signal. But again, there is some limitation. Okay. So the power in the sideband depends upon the value of modulation index. That's right, as you can see here, it's m squared, all right, divided by 4, m squared divided by 4. So it's directly related to modulation index, and the greater the percentage of modulation, the higher the sideband power. Okay, if you remember from previous class, we said we have 3 scenarios related to modulation index. Either modulation index equal to 1 or greater than 1 or less than 1. All right, so 3 scenarios. So we can apply 3 scenarios here in order to, determine the power. Okay, but definitely the best scenario when modulation index is less than 1. All right, modulation index is less than 1. All right, so maximum power appear in sidebands when m equal to 1. All right, m equal to 1. The power in each sideband can be represented. Again, the power for upper sideband equal to power for lower sideband. Then we can use, the previous formula, k a sub c squared, m squared divided by 4, then m equal to 1. Then we can find this is the maximum power for both upper sideband and lower sideband equal to p sub c divided by 4. All right, so which means that when the modulation index equal to 1, the power in each sideband is 1/4 or 25% of the carrier power. All right, of the carrier power. All right, so for example here, if we have 25%, so that means we have 2 sidebands. All right, their power put together to give 50% of the carrier power. So that means in double sideband large carrier, if the modulation index is 1, so that means the power will be for both upper sideband and lower sideband will be 50%. All right, will be 50%, each 25%. 25 for upper sideband and another 25 for lower sideband. Okay, guys, clear? Is there any concern, any questions so far? Okay, good. All right. So the ratio of useful power inside bands to the total power, normally we call it power efficiency. All right, power efficiency, which is sideband power divided by total power. Then we can just divide sideband power, which is m squared divided by 2. When I said sideband power, that means this one. All right, this is for upper sideband, this is for lower sideband. Then if I do summation, I will have m squared over 2. All right, m squared over 2. It's not for one sideband, for both. So that's why I have m squared over 2, not m squared over 4. Okay, sidebands power, both upper and lower, will be m squared divided by 2, divided by the total power that we have determined, which is this one, 1 plus m squared divided by 2. Then this is the what we call it the power efficiency, m squared divided by 2 plus m squared. All right, so as you can see, normally the power actually is directly related to the modulation index. All right, related to modulation index. And from here you can we can check, for example, the limitation behind adopting double sideband large carrier. Because as I mentioned that there's no information related to the modulating signal or the original signal or the transmitted signal inside the carrier frequency. So we have only power located at the carrier frequency, and definitely this one is the we are going to waste some power. Okay, as you can see here, the carrier terms does not contain any information about the message signal. Therefore, the power expanded in this carrier is wasted, all right, for any transfer of the information. It's just a wasted power. So we have another technique. We call it double sideband suppressed carrier. We can remove the carrier in order to improve the power, all right, at both upper sideband and lower sideband. All right, again here, for example, if m equal 1 modulation, that means the power efficiency will be 33% power efficiency is achieved. All right, that means only 1/3 of the transmitted power. Why? Here, if you have m equal to 1, then we have 1 divided 1 plus 2. All right, so 1/3. All right, 1/3 of the overall transmitted power. The remaining actually will be inside the carrier. But again, why we need to use double sideband large carrier? So this is the price that we need to pay for cheap detector, all right, for cheap detector or cheap modulation. In order to detect the transmitted signal by using double sideband large carrier, we can do that by a very simple electronic circuit, all right, very simple electronic circuit. One diode with one resistor and one capacitor. That's it. We can receive the transmitted signal, all right, which is very cheap, all right, not cost, and very simple to design. All right, so now we will discuss the generation and detection of full AM, all right, generation and detection of full AM. Again, when I said full AM, that means double sideband large carrier, all right, this one equal to double sideband large carrier, all right, sorry, double sideband large carrier. All right, so now when I said generation, that means it's modulation. So this one will be modulation. All right, this one generation, that means modulation. And when I said detection, will be demodulation. All right, so modulation and demodulation. Okay, guys, my voice is clear, guys?
Yes, sir. Yeah.
All right.
Very clear.
Yes.
So both generation and detection required multiplication to be performed. What we mean by multiplication? So we have two signals. All right. you can remember that the full AM, or what we call it double sideband large carrier, the expression, which is A sub C, all right, 1 plus M cos the frequency for modulating signal multiplied by cosine the carrier frequency. All right, so this is the general expression. So when I said multiplication, that means we need to multiply this one, the carrier frequency, with the modulating signal. All right, the procedure is very straightforward and very simple for the whole technique in amplitude modulation. So the multiplication normally is achieved by using a network with non-linear characteristics. All right, non-linear characteristics, as we will see afterward. Okay, so for example, if we have the first technique, we call it square law modulator. All right, square law modulator. We have 3 components. All right, in this modulator, we have summer, summing the carrier and modulating signal, and we have non-linearity block, which is square law. All right, square law, and definitely we have the characteristics of this non-linear or non-linearity block. And after that we have band pass filter. Band pass filter, all right, centered at the carrier frequency to extract the desired modulation products. All right, so 3 main components. We will explain one by one. So let's see how we can generate by this square law. So this is the block diagram. This is the block diagram for square law modulator. As we can see, we have summer. We need to do summation, modulating signal with carrier signal. We have adder here. All right, hardware component adder. Here we have V1 of T. V1 of T, the output from this adder. And after that, we have the second component, which is non-linearity or squared law device. Squared law device, we can generate V2 of T. And the last component, we have band pass filter. Band pass filter at the carrier frequency. This is the cutoff F sub C. All right, where the bandwidth definitely will be 2B. Why the bandwidth 2B? Because if you remember last class when we said that the bandwidth for the modulated signal will be twice of the transmitted signal. All right, so that means this bandwidth, the bandwidth for the band pass filter will be 2B to cover both upper and lower side band. Okay. Then we have the characteristics of square law nonlinearity. This is the mathematical formulation for this device. All right, this is mathematical formula for this device. So once we have input, the output will be A1, which is constant, V1 of T, V1 from here. All right, the result from summer, plus A2, which is constant, V1 squared of T. That means this one also square. After that, once we done simplify, all right, then we pass the signal through the band pass filter, then definitely we can extract the require the desired signal. Okay, so this is V1, this is V1, this is V1, which is summation of carrier signal S sub C, all right, C for carrier, and here modulating signal, all right, M from modulating. Then we have, if we replace the carrier by sinusoidal signal, which is A sub C cosine omega CT, plus the modulating signal, which is SM of T. Definitely this one, you can replace it by M, or you can replace it by AM, all right, AM cosine omega M T. All right, you can replace it by this one, but for simplicity, we make it the modulating signal S sub M of T. That's it. Then we need to pass this one, V1, by the non-linearity square law. All right, non-linearity square law. This is the characteristics. Then V2 will be A1 V1. We multiply this one by A1 plus we need to square this one. All right, V1 square. All right, it's not difficult. So the result for this procedure, I mean, after the non-linearity device, this one will be V2 V2 of T will have A1 after I multiply and simplify. All right, multiply and simplify because I'm looking for omega C. All right, looking for this one, omega C. Why omega C? Because this is the cutoff for my band pass filter. You remember this one? All right, this is F sub C. That means I need to find the terms with F sub C only. Then I arrange it. This one, A1, A sub C, cosine, after we, squared and rearranged, omega sub CT plus 2, AC, A2, modulating signal multiplied by cosine, omega CT. This one, the desired signal, you can see omega C and omega C. Omega C can be replaced by, what we call it, the F sub C, all right? And the unwanted term, we have this one, A1, all right, S M of T plus A2 squared, M of T plus A2 A sub C squared, and here we have one missing term, which is S M of T, all right, times cosine squared omega CT. So this is V2, the output from nonlinear device. Okay, so how many terms we have? We have number 1, number 2, number 3, number 4, and number 5. Then this one, again, I have one formula from relation. From relation, cosine squared will be 1 plus cosine 2 omega CT divided by 2. Okay, and this one multiplied by SM, again, of T, one missing part. So now we have altogether 6 terms. So if I would like to draw the spectrums, again, from Fourier transform pairs, all right, for example, in this chapter, we're going to use only this one, Fourier transform, all right? No need, to solve Fourier transform. It's not like chapter 2. We already learned from chapter 2 Fourier transform. Then we take only these 2 Fourier transform pairs, okay? Cosine will be half. And if we have, for example, message, SM of T multiplied by cosine, then we'll definitely have this one, for example, upper sideband and lower sideband. So if you'd like to draw the spectrum, okay, so I will take this one, omega C, this one at F sub C, all right, what's the amplitude I have? After I use this formula, will be divided by 2, all right, because I'm moving to frequency. Then if I apply this formula, this one will be A1 AC divided by 2, all right, F minus F sub C plus sigma F plus F sub C, all right, so this one, the upper, this one, the lower, this one, the origin frequency, okay. Then number 2, also I have omega C, then also I can apply this formula, then this formula will be same, divided by 2, here we have M, then also will be located at this one, this is number 2, okay, this is number 2. And for example, number 3, I have only original signal. Original signal, if you remember the first slide, when we, we're discussing about the baseband signal. We said the baseband signal, it's just, normal signal located at the original when frequency equal to 0, all right, without any shifting in frequency. So this is the original signal, and this is shifted, original signal squared, so that means with, some broad band compared to number 3, And number 5, after I multiply this one, all right, the original signal divided by 2, which is here, all right, original signal divided by 2, and we have 2 WC, that means 2 F sub C, which is, I mean, very far from this one, okay? Then what I need now, I need to generate AM signal. So AM signal normally comes with modulating signal together with carrier frequency, all right? So that means only this one will pass through my band pass filter, this one and this one, 2 terms only. Okay, guys, clear this one, please. Any question? Any question, guys? Ahmad Hassan, do you have a question?
Yeah, actually, the last part of drawing.
Okay,
So, what we gonna benefit from it?
all right. So now you can see, all right, we need to generate full AM signal. All right, we need to generate full AM signal, double sideband large carrier. All right, double sideband large carrier. So how we can do that? How we can generate double sideband large carrier? We said we have square law modulator. All right, square law modulator. We have 3 components: summer, non-linearity block, and band pass filter. And this is the block diagram, and this is the characteristics of what we call it, band pass filter. All right, so once we apply at the output here, definitely we will have double sideband large carrier. So after we simplify, after we multiply, and after we squared, we need to consider this one, the cutoff frequency of band pass filter, all right, at the origin F sub C. All right, then if you can take, you can see this one. All right, this term 1 plus 2 will generate a double sideband large carrier. All right, double sideband large carrier. I can simplify this one. All right, I can write it or rewrite it. This one, I have AC. All right, I can take it 1 plus A2 SM of T multiplied by cosine omega CT. All right, so this is the general expression for double sideband large carrier. Am I right? Double sideband large carrier. So this is the technique how I can generate. All right, how I can generate. Definitely this one, the constant, we can do it by assumption. All right, this one we can assume it equal to 1. This one, I mean, equal to something in order to make it exactly same as the original one. But from here, if you can simplify, you can take this one as a common. All right, this one as a common. I can make it 1 plus the modulating signal Sm of T plus cosine omega CT, which is same as we, I mean, explained in previous slide, if you remember. All right, this is the general expression. This is the general expression that I said. You can see this one. All right, then by using square law modulator, I have to generate the exact signal, this one. All right, A sub C 1 plus A cosine 2 pi FMT times cosine 2 pi F sub C T. All right, so from here the output must be double sideband large carrier, same expression. So from here, definitely 1 and 2 will pass through our band pass filter, and this one can be simplified, and the result will be exact double sideband large carrier. Is that clear, guys?
Yes, sir.
Any other concern? Any other question, guys? Avan, clear this one?
Yes.
All right, Harish, clear?
Yeah, it's clear, but only the picture, this drawing.
All right.
Why did you put why did you put number 5 there?
Number
sorry, number 4.
Number 5. Which one? Ah, yeah, number 5. This one you have, as I mentioned, this one, number 5. We have what you call it here, SM. SM of T. All right.
Yeah.
SM of T, because I said here we have one missing. All right. Here should be SM of T. All right. Which is original at the origin because it's a baseband. All right. Baseband. Then, and if you take it, for example, here I remove SM of T, I have only A squared divided by 2, which is definitely will be at origin. But even if you put AM will be at, at origin, because what you call it, baseband signal. Baseband signal. After we multiply this one, because this one I can make it like that, am I right? SM A sub C divided by 2. Okay, 1 plus cosine 2 omega sub c t. All right. Then if I multiply this one by 1, there's no more carrier frequency. Will be original signal, modulating signal. Am I right? So you can put it here at origin 0 because it's a baseband signal. Baseband signal at origin.
Okay, yeah.
Yeah. All right.
Original.
Yeah.
Yeah. Yeah.
All right. Lavan, do you have any question?
No, sir.
Hanas, any question?
No, sir.
All right. Shalao, any question? Mehvan, Ahmad Naif, any question, guys, please? All right.
No, sir.
All right. All right. Then this one, as I mentioned, this is number 1, and number 2 will be the double sideband large carrier. So that means by using this technique, squared law, all right, I can generate the signal, which is double sideband large carrier. So in order to make it exactly same as the original one, we can do some assumption. As you can see here, we assume that A1 equal to 1 and A2 equal 1 divided by 2 AC in order to make it similar to the original one. All right, in order just to simplify and make it similar to original one, AC1 plus M. If you remember M, modulation index, which can be written as AM, all right, divided by AC. AM divided by AC. So that's why I assume that A2 equal 1 divided by 2 AC, 2 in order to remove this 2. Okay, in order to remove this one. All right, I have 2 here, 2A sub C, in order to remove this one, and divided by AC because I need to make it as a modulation index, which is AM divided by AC. All right, AM divided by AC. So in this case, this is my full AM signal, which I really generated by using square law technique, square law modulator. All right, square law modulator. Okay. So the interesting point in this double sideband large carrier, that same technique, square law modulator, I can use it as a modulator and also as I can use it as a detector. All right, I can use it as a modulator and also I can use it as a detector. What I need to do in order to detect or in order to modulate, I need just to change this one. Previously, I have what you call it band pass filter. So if I remove band pass filter and I replace it by low pass filter, then I can detect the modulating signal. All right, I can detect the modulating signal. What do you mean by modulating signal? That means this signal, original signal, this one. All right, cosine omega mt. All right, so this one square law device can be used as a modulator. If I have band pass filter, if I replace the band pass filter with low pass filter, then I can use it as a detector, all right, as a demodulator, by using low pass filter with cutoff frequency FM. Why FM? Because I need to detect this one, all right, my modulating signal, all right, not carrier. I need to detect only the transmitted signal, FM. I mean, not FM, I mean F sub M, which is, I mean, the frequency for the modulating signal. So this is the block diagram. I have AM signal. If I said I have AM signal, how can I write my AM signal? This is AM signal, all right? A sub C, 1 plus M cosine omega mt multiplied by cosine omega sub t, all right? Then I move it to nonlinear device. Same, what's the characteristics of this nonlinear device? Exactly same. Here, exactly same. This is the output V2. I need to take A1 V1 of t plus A2 V1 squared of t. So that means same characteristics, same properties. All right, and after that, I pass my signal to low pass filter. All right, low pass filter. Okay, low pass filter. Then let's go back and see if I have here low pass filter. If I have here low pass filter with cutoff frequency F sub M, again, I missed this one here, should be SM of T. All right, SM of T missing. Here should be SM of T. All right, so same. Now if I multiply this one, the result will be SM AC squared A2 divided by 2, all right, plus this one multiplied by cosine 2 omega c. Okay, so if I pass the whole output through low pass filter, cutoff frequency will be at FM. So that means I need to find only FM. So which term? I need to track this one. Here we have F sub C, I don't want. Here we have SM, but also we have omega sub C. Here we have only SM, all right, only SM. And here we have A2M squared, all right, and here we have SM with the amplitude, all right, A sub C, okay, divided by 2. So when I pass through low pass filter, then I will take only this one. I will take only this term, all right, which is at the origin, this one, all right, at the origin, at the 0, which is the baseband signal, all right, baseband signal. So this is the, I mean, the advantages of this technique, square law, what you call it, the square law technique, where we can use it as a modulator in order to generate double sideband large carrier, or we can use it as a detector in order to demodulate, in order to recover the original transmitted signal, which is, I mean, modulating signal, SM of T, SM of T. All right, then here I have, I mean, solve it by, I mean, here I have, I mean, using some relation instead of using full AM. Then you can, I mean, refer to this one. I mean, either way, you can use either this one or you can use the one that we have solved here, which is as usual. You can take just full AM signal, and after that you use the properties of non-linearity device and pass the output to low pass filter with cutoff frequency f sub m. Then definitely you will receive the transmitted signal, which is AC, for example, divided by 2 multiplied by Sm of t, multiplied by Sm of t. Okay, guys, clear this one, the square law, modulator and demodulator. Square law, modulator, same, can be used as a modulator if we use band pass filter, and same can be used as a detector or demodulator if we replace band pass filter by low pass filter. All right, by low pass filter. Clear, guys? Is there any question? Mehvan, you have question? Hani, do you have any question?
No, sir.
All right. Then another, if you don't have any question, then we have another technique in order to detect. We have another technique in order to detect the double sideband large carrier. Double sideband large carrier. This technique, actually, we call it envelope detector. All right. This technique, we call it envelope detector. Okay, guys. So which one here? So we have this one actually is a modulated signal. Modulated signal, mu equal 0.5. That means the modulation index. All right. This one, same as modulation index, is 0.5. That means less than 1. All right. So that means this is the best modulation index. All right. Best modulation index when the modulation index is less than 1. And the ideal scenario, we said m equal to 1. And if we have, for example, the distortion, if we make its modulation index greater than 1, will be, distortion is very difficult to recover the modulating signal. Anyway, so this is, how it looks like. So if we have, some experiment with oscilloscope, then we can see at the oscilloscope, this is how the signal looks like. All right, how's the modulated signal looks like. As you can see, this one we have 2 frequencies, am I right? This one is very high frequency, so that means this one will be carrier frequency. This one for carrier. Why? Because it's high frequency. And this is for low frequency. Definitely will be for modulating signal, Sm of t. Okay, so from the signal how it looks like, we can determine, because here we have some high frequency, then this one will be for carrier, and this one will be for modulating signal. All right, modulating signal. Anyway, so we can see this one. Why we call it as an envelope? Because here it looks like an envelope. All right, here the signals comes with the carrier. The amplitude of a carrier frequency is vary with amplitude of signal. All right, but with different frequency. Okay, so the signal, modulating signal, it's located here in this part. All right, here, here, and here. All right, and here. All right, the modulating signal, the original signal. So if I can detect, all right, if I can, for example, use this one envelope detector by tracking only the top of the modulated signal, this one, the top. All right, this one. If I can track this one, the amplitude, all right, of the top, then I can recover the transmitted signal or the modulating signal. So how can I do that? By very simple circuit. You can see this one, very simple circuit. This one Vn, which is double sideband here, double sideband, large carrier modulated signal. I have diode and I have a resistor with capacitor. All right, resistor with capacitor. This one we call it envelope detector. This one we call it envelope detector. And I have another circuit here is connected to another resistor with another capacitor. This one RC filter. All right, RC filter, which is low pass filter. Why I need to use low pass filter? In order to smooth, to smooth the amplitude after I detect. All right, after I detect the envelope, then normally I can use low pass filter in order to smooth. Okay, so how this circuit works? It's very simple. So since I have diode, so for those students, done with electronic circuits, knows how the diodes work. All right, so diodes actually is electronic device that allow current to pass through one direction. All right, one direction only. So that means once this signal, it's varying positive and negative, pass through this diode, I have only the positive parts. Why? Because if the signal pass through this direction, the positive side of signal, this diode will be forward bias. So that means the current will pass through. And if the signal comes from the negative side, all right, this direction, then the diode will be reverse bias, open circuit. Then that means the output will be only the positive part, only the positive part. Okay, so this is number one. Number two, if I have only positive parts, let me check with this one, yes, okay. Then now the advantages of using RC, the resistance and capacitor. So I have only this one, only positive parts. For example, assumption, just assuming like this, all right. Then when the voltage actually starts rising, of this one, when the voltage starts rising, the capacitor gonna charge, all right? And when the voltage starts moving down, the capacitor will discharge. So this one, the capacitor will charge, all right? And after that, the capacitor will discharge. Once the signal is raised again, the capacitor will charge, and once the signal fall down, all right, the capacitor discharge. So this actually will continue charging, discharge, charge, discharge, again and again and again until, all right, we can recover the modulating signal. All right, we can recover the modulating signal. Okay, so this is how the principle of working. So I have diode. The diode actually is very simple electronic device that allow current to pass through only one direction. All right, only one direction. The other direction definitely will be like an open circuit. All right, so in this particular case, it looks like a clipping circuit. So I'm gonna clip all the negative part. I have only positive part. All right, with separation, positive part. Then when the signal actually is rising up, the capacitor will charge. All right, the capacitor will charge, and after that, when the signal actually is moving down, the capacitor discharge. Okay, so very important note again, if you'd like to design this circuit, is the time constant. All right, time constant of the capacitor, or what we call it, if you remember in circuit theory, time constant, which is tau. All right, tau, time constant for the capacitor. This one actually must be really selected to be not too high, all right, and not too low. So if it, very high, then the discharge will take long place, all right, then I'm gonna miss some important information. And if it is too low, then I'm gonna detect the carrier itself, not the message signal, all right, I'm gonna detect the carrier. So that means it's in between the time constant of the capacitor, then I can really detect only the top of the what we call it, the envelope, which the message signal actually located in this area only. Okay, guys, clear this one? Any question related to envelope detector? Guys, any question? Yes, Shalom?
I don't have any questions.
Sorry, Shalom? Guys, any question? This one, Mardi,
Sir,
for today.
No.
let us read, then we might have questions
All right. Okay.
later. I mean,
Oh, no problem. Okay. Okay, Martin. Actually, we have to continue because my plan actually is to finish this chapter by this week, and still I'm preparing some tutorial sheets with 9 questions, if I'm mistaken. So also we have to discuss the tutorial, how we solve, for better understanding. So let me take, let's say 10 more minutes. All right, and after that we can finish this class. I know, it's very difficult. It's very difficult to, go online classes for such subjects, which really we need to, track students one by one. But again and again, we are in abnormal scenarios, and we need just to practice patient. Okay, guys, let me ask you the last question. Yes, sorry.
It's not like a normal class watching computers. It really hurts my eyes because
Yeah.
I did surgery for my eyes.
Yeah, I know that, but what to do? As I mentioned,
So
just to
1 hour for online class is enough, wallah.
yeah, I know it's very hard. It's very hard, not only for you guys, but only for me, because I feel just just talking with a PC. All right, I'm just keeping watching, and so it's really difficult because this is a new experience to all, not only you guys, but also for us as a teacher. But again, what we need to do just to practice patient, and we'll try our best. Okay, guys. So again, this is what we call the envelope detector, all right, which is very, very simple circuit. Very simple circuit. We have diode, resistor, capacitor. All right, it costs nothing. All right, it costs nothing, but it's play very important role in AM amplitude communication in order to detect the double sideband large carrier. Double sideband large carrier. Okay. So the second the second technique, double sideband suppressed carrier. All right, double sideband suppressed carrier. As I mentioned in the previous technique, we have double sideband large carrier, so that means the carrier will be presence. All right, in this particular scenario, we're gonna suppress the carrier. We're gonna remove the carrier. All right, and definitely the power will be distributed to power both upper sideband and lower sideband. The power will be distributed to both upper sideband and lower sideband. All right. So again, this one, it's almost similar to the previous one, but the way that we're going to generate the signal will be a little bit different. So for example, here we have carrier signal, and we have modulating signal. This is the carrier in terms of omega c. This one, the modulated signal in terms of omega sub m. Then I need to do multiplication. All right, the modulated signal is simply the product of these two signals. If I multiply this one directly with carrier, all right, the signal directly with carrier, then I have, this is the result. All right, where's carrier? There is no carrier. Compared to double sideband large carrier, if you remember, we have A, C, all right, 1 plus SM, all right, cosine omega ct. So in this case, we have 3 terms. This one, number 1, and SM multiplying by cosine related in 2 terms. So that in double sideband large carrier, we have 3 terms. The first one actually is the carrier itself. All right, carrier itself, which is this one, A sub c times 1 times the cosine, which is missing in this particular technique. All right, missing or suppressed in this technique, which is double sideband suppressed carrier modulation. So again, this is upper sideband and this is lower sideband, but we don't have any carrier signal. We don't have any carrier signal. So this is the block diagram, which is very straightforward. Block diagram, we have modulating signal, and we have local oscillator or frequency generator to generate the carrier. Then we multiply products, all right, together, and after that we can generate the double sideband suppressed carrier, double sideband suppressed carrier. But definitely there are some frequency shifting. You can see frequency shifting. It's not at the origin, frequency shifting. All right, and this is the frequency domain representation. Frequency domain representation. You can see we have only upper sideband and lower sideband, and the bandwidth definitely for double sideband suppressed carriers will be same as the bandwidth of double sideband large carrier. All right, which is twice of the modulating signal. So again, in this technique also we need to do generation and detection. That means we need to generate double sideband suppressed carrier, and also we need to use some technique in order to detect double sideband suppressed carrier. So in terms of generation, we have what you call it, the balanced modulator technique. All right, this is the block diagram. Balance modulator, you can see this is the modulating signal. All right, modulating signal, and this is positive in this direction and negative in this direction. And after that we have AM modulator. We need to multiply by carrier frequency, and again this one carrier generator or local oscillator, or we call the frequency generator. This will multiply by both sides. Then we have S1 of t and S2 of t, and we need to do summation. All right, from here sum or subtract. Then we can generate what we call a double sideband suppressed carrier. Double sideband suppressed carrier. Okay, so this is S1 of t. All right, and this is the second S2 of t. When we have minus, then you can see this one is plus and this one is minus. Then after that, the signal will be S1 of t minus S2 of t. Then we can reach to this signal. All right, which is definitely SM, and modulating signal times the carrier, which is double sideband large carrier. All right, double sideband large carrier. Okay, guys, clear? Guys, clear this one? Balance modulator. You want to stop here or you want to continue?
Sir, time is over. What to continue?
Time is over.
Yeah.
All right. Who's that? From Shalom? All right, let us study. All right.
Well,
Okay, no problem, no problem. All right, so do you have any question related to this one, guys, please?
no.
Balance modulator. Any question, any concern?
No, thanks.
Okay, Mardin, Ahmad, Levan, Balant.
No, sir,
No.
thank you. You don't have anything.
All right, so for today we have a quiz, okay?
No, sir.
We have a quiz
Yeah.
for Harish, Hanas,
Yeah.
Mehvan, Lavan, and Ahmad Hassan, if I'm not mistaken. Am I right?
Yes.
Yeah, all right. So,
What about me?
sorry?
What about
Your voice is not clear.
Sir, I said, What about me?
Yeah, you are Hani.
My-
Okay, Hani on Tuesday.
Okay.
All right, we have 5 students today and 5 students on Tuesday. All right.
Okay, great.
Okay, sir. Sir,
Okay, guys.
but one question.
Okay.
Uh, sir, is this for increasing the grade of the previous quiz?
Sorry, Shalom.
Is this quiz for increasing the grades of last quiz?
Yes, yes.